Greetings, differential equations scholars, and welcome to the first in a series of videos on section 7.1, where we introduce the concept of Laplace transforms. Ultimately, as we're going to find in chapter 7, Laplace transforms can be a valuable tool for helping to solve initial value problems. But before can use them as a tool for helping to solve differential equations, we first have to learn just what they are. So to help motivate this, you'll see we have a question in the middle of the screen here. We've got an integral expression, and the question is, what value does this integral expression right here have? We can see that that is in fact an improper integral because its upper limit is infinity. So this is an integral over an unbounded region. And that integral, the value of that integral need not exist if the area underneath that curve is infinite. But sometimes, as you learned in your previous study of calculus, sometimes such integrals will converge to a particular value. So the question we're going to ask here is this particular integral, and you can see that in it we're integrating with respect to the variable t, but there's also a variable s that appears in the integral. What value would we get if we take the function f of t specifically to be the constant 3 here? I'm interested in exploring, does the value of this improper integral exist? Does it converge to a particular value? And if so, what is that value? So here's our integral. You see here we've just taken this expression here and I've replaced f of t with the constant 3. And we're going to see if we can figure out what value this improper integral might have. Well, the first trick in doing that, of course, is to interpret what we mean by an improper integral whose upper limit is infinity. And you might remember that how we interpret that is that what this really is it's a limit. It's a limit if we replace that upper limit with, say, b, and we ask, well, what is the limit of that integral as b goes to infinity? That's our interpretation of the meaning of that improper integral. Well, now that we've got that integral here with the infinite limit replaced with one with a finite upper limit b, we can take a look at what we get when we do that. So let's go ahead and now find the antiderivative for that. Well, that's an exponential, and since it's an exponential whose exponent is negative st, and we're integrating with respect to t, that's going to simply mean that our antiderivative here is going to be negative 3 over s times e to the minus st. That will be the antiderivative that we will arrive at. And of course, we want to use our fundamental theorem of calculus and evaluate that at its limits. That means we're going to replace the upper limit with t equal to b, and that'll give us negative 3 over s times e to the minus bs. And then we're also going to replace at the lower limit t with 0. And you can see that if we replace t with 0, then that exponent becomes 0. And we're going to have minus 3 over s times e to the 0. And of course, we're subtracting that because of the fundamental theorem of calculus. So that becomes a plus there. So now after we've replaced at the limits, the question is, well, does this limit exist? Now that limit has, the expression that we're taking the limit of has two pieces to it. The second piece is just 3 over s. And since s is constant here, since s isn't moving, um, that piece of the limit certainly does exist. But what about this first piece here? What about this expression right here? Does that piece have a limit as b goes to infinity? Well, for the moment, let's assume that s is greater than 0. We haven't put any restrictions on s so far, but let's assume for now that s is positive. If s is positive and b is positive, well, after all, it's approaching positive infinity. If s is positive and b is positive, then we can see that the exponent negative b times s will be negative. And so we'll have an exponential function e to the minus bs with a negative exponent. And that negative exponent is going to essentially decrease without bound. And that means that this expression e to the minus bs as b goes to infinity is going to indeed approach 0 because of the properties of the e to the negative x function. So that piece will approach 0 as b goes to infinity, provided s is positive. So what does that now mean about our limit? Well, using our properties of limits, we can take this expression here, minus 3 over s, bring it to the front, and we say that our limit is minus 3 over s times the limit of e to the minus bs plus the limit of 3 over s, which is 3 over s. And now, since this expression here is going to approach 0, since that expression right there is approaching 0 in the limit, that in fact means that that first piece is going to approach negative 3 over s times 0, which is 0. And we've deduced that that limit is in fact 3 over s. It does converge to a value of 3 over s, provided we assume that s is greater than 0. Now that assumption is actually critically important. We only will have convergence to that 3 over s if s is greater than 0. Indeed, if we go back and you think about the original integral that we had, and you imagine, well, just what does it look like if s is a negative value? Think about this original integral here if s was negative. If s is negative, then negative s is positive. And we have e to some positive constant times t. In other words, we have the function essentially e over x being integrated between 0 and infinity. It's pretty obvious to see that that integral is going to diverge. There's no way that the area underneath the curve e to the x is going to be finite as we let the upper limit go to infinity. We're just going to keep having increasingly more area. So we can see that that integral diverges if s is negative. It also diverges if s is 0 because we end up integrating a constant function over an infinite region, and that certainly doesn't have finite area. So what have we found? We've found that that improper integral that we started with converged, provided s was greater than 0, to an expression, to a function of 3 over s. Now, remember that that was what the integral converged to when we took the function f of t to be 3. So here's what we're now going to say. We're going to use this expression here, a script L. That script L refers to a Laplace transform. And what we're going to say is that when we evaluate that particular improper integral expression with f of t equal to 3, we get the function 3 over s. And so that is what we refer to as the Laplace transform of the function 3. What that integral did was it took a function, the function 3, which we substituted into our integral at the beginning, and it transformed that constant function 3 into this function of s, 3 over s. So we call this an integral transformation. When we substitute in a particular function into the integral, what comes out, provided we have appropriate restrictions on s, is a function of s. And we refer to this function over here as the Laplace transform of this function over here. In general, you can use this same logic that we just used. You can replace our 3 with any constant k that you want. And just as we've shown that the Laplace transform of 3 was 3 over s, you can use the same logic from this example just to say that the Laplace transform of any constant k is going to be k over s. So that's a first example of using the definition of the Laplace transform to find the Laplace transform of a constant function. We're going to continue to explore that definition. In the next example, we'll take a look at the Laplace transform of a function that isn't constant and see what arises when we do that. I hope this example has been instructive to you all. Stay tuned, coming up for another video demonstrating the definition of the Laplace transform.